Hello everyone, welcome back to Tax Riders. In this video we want to continue our discussion on the finite element theory, and we want to have a look at variational formulation of partial differential equations. Let's go for it. So in the previous video we started to talk about the theory of finite element. I said that we want to cover the essentials only, and those are actually what you need to know when you want to work with tools like Phoenix and FreeFem. So for this repository, I told you before, you can find a link in the description, or you can go to Tax Riders website and you can go directly to GitHub, or you can go to publish videos and easy introduction to applied numerical computing, and then here it's the material in this repository, and then you come here. So for the finite element method, in the previous video, we talked about function approximation, and I told you that that's actually the basic, the most essential thing, let's say like this, that you need to know about finite element approximation, about finite element solution of equations, and that was actually approximation of functions. And in this video, we want to talk about approximation of differential equations. And when we want to do that, you will see that it is very simple. Again, very similar to what we did in the previous video, but you will see that we need a variational formulation of the equation. And you will see the reason in this video in a couple of minutes. So I opened this chapter as a Jupyter notebook. So, and the variational formulation, before going to that, I want to show you something, because, this is something that we have already discussed in previous videos of, let's say, for finite element modeling. I can go to YouTube and then show you the series. So on the playlists and introduction to finite element modeling. So these are the video that we had for, solving a single problem in different programs, in different finite element tools. And the video number 4 and number 6, we used FreeFem and Phoenix, and for those tools we needed to derive a weak formulation of the equation. If you remember, if you haven't watched the video, please watch it. That's actually, in those videos you can see the main approach, or let's say the main workflow that we usually need to do when we want to simulate something with finite element, simulate an equation. So in episode 4, we have the weak formulation here, and this is the file that we had. I want to keep it open here, because that was actually we wanted to start to derive the equation, the weak formulation of this one. Of this equation, that was heat diffusion equation, and then I described what we needed to do. Part of this whole process is already discussed. The theory behind, is already discussed in the previous video, and in this video we want to continue to the main point that we need to know about weak formulation. And then I come back to this file, and then I will show you the things that we did here and the similarity between the. I want to show you that these are the theories behind what we did in this PDF file, in this kind of model. So variational formulation, it can be with global basis. Here we see that it says with global basis functions. Meaning that the concepts of basis function, the orthogonal ones, and then similar to basic vectors, and then when we use Lagrange polynomials, it becomes finite element. So that's more or less the same thing. So for differential equations, we have an equation like this: LU equals 0 and U is unknown. So here in this case we wanna get the function actually like this in this one-dimensional differential equation. If it is 0, then it means that the second derivative of u respecting to x equals f of x. And then it can have also a diffusion. It's a kind of diffusion coefficient, but it can have also a coefficient here, which in this case makes it non-linear, but it doesn't matter at this point. And it can have the boundary condition like bu equals 0 when x is 0 and b equals 0 also when x equals L. So it's a one-dimensional case, and we want to have like with the length of L. We want to have the solution of u on that. So depending on the type of B, it can have, there are different types of boundary condition. These are the three main ones that, the most commonly used ones. We have Dirichlet boundary condition, or Dirichlet. That is actually a linear one, meaning that you have, like, if it is 0, meaning that you have the value of u on the boundary, or you have the value of the derivative of u on the boundary. In this case, you can see the derivative is equals to g, and in the Robin condition, you can have a mixture of the Neumann and Dirichlet. You have the derivative and the defined value both at the same time. So let's go on, and then we will see that in this case, I think it tries to solve the equation analytically. We don't want to discuss this. We have already discussed that in the SimPy video. So this is the analytical solution. So yeah, let's just skip this one. It is for demonstration cases when we want to compare the numerical solution to the exact solution. But this is important. When we want to have the residual, the concept is very similar. That this is actually, we define a space of various basis functions here, and then we want to have like the approximation. This is what we know already. This is the type of approximation that we use, which is actually a summation of some coefficient multiplied by those basis functions, and then we have the residual. And then using various techniques, least square method or Galerkinian projection, we want to minimize this error. So in the least square, you know that we want to minimize the error, which is actually the inner product of the error by itself, and we want to minimize it. And in the Galerkin method, we want to minimize, or we want to make the residual perpendicular to the approximation, which is actually the method of weighted residuals, more or less the same. So you can see that in this case, we can say that residuals, which was actually what we used in the previous video, inner product of that to the psi of I, which is the basis functions for all the basis functions belonging to the space with the discretized space, is 0. So this is actually where the story starts, and generally here it says that equations like this one or this one are called the weak formulation. So when we start from this, so this is, as I said, this is where everything starts. When we start to expand this inner product of the residual and the basis function equals 0, then we are actually doing the weak formulation. But later on, you will see that for higher order differentiation, for derivatives, it becomes a little bit tricky, and that's why we always say that we need to have like the weak form or the variation of formulation of the equation. So it says that it's the terminology, and then this is something that is used as an alternative to the strong formulation of a differential equation, which is actually the main equation. So, two important concepts. We have test and trial functions. So, as you can see here, we have test as first trial. So, trial functions are actually the function that we approximate. So, in this case, u is the approximation. It belongs to the trial function space, and the basis functions that we use to approximate the main function, and then we find the coefficients. So all the basis functions are actually test functions. So let's say that generally the test and trial function space can be the same, or they can have different properties. They can belong to different spaces. For example, in implementation, they usually belong to the same space, but when you want to derive it, when you want to, for example, work with mathematical equations, they usually belong to two different spaces, and they have different properties. So for collocation method, it's again similar, but it uses delta Dirac function. Yeah. So yeah, I don't want to discuss this one. This is similar to the Galerkin method. But it is actually, you know, the same concept, that it is because delta function has all similar properties to, for example, Lagrange polynomials, that they have like, they are non-zero only in one point of space and zero elsewhere. So it can be also a nice basis function, which is not used by finite element. So this is an example, you know, that we are not in this notebook. That was for the global functions. Global basis function. So in this case, this is the basis function that we're going to use to solve this equation. So it has all the properties that we want. You can see that we can choose psi I, the test functions for v. So these are the test basis functions that we use. And then these are the boundary conditions that can be approximated. And we want to actually approximate the solution of this differential equation. So we go on, and then we write the residuals. It can be also written using least square method. You know it. We want to have like the residuals equals to zero. Error equals to zero, and then we go on. So it becomes something like this. So this one, you can again see that this is A and this is B, and we want to approximate the value of the coefficients. And by doing that, we can easily find this approximation of the differential equation. But here, the problem arises that it is actually we have the second derivative of the basis function. So you may see the problem, the challenge that we will have here, but later on it will be discussed. So in this case, there is no problem because we have like sinusoidal basis functions that can be the second derivative can be calculated. But when we go on with the finite element, you will see that it is not possible, because if you remember, we use like those kind of piecewise functions that they do not have the second derivative or the first derivative, because the second derivative is undefined. So yeah, this is the implementation for the basis, the kind of basis function that we used. This is the basis function, and then for the Galerkin method, you know that we have the inner product of the function, in this case the differential equation, to the test function, and actually the approximation itself. So after having something like this is, as I said, this is bilinear term and this is linear. We say that later on you will see that because it's it contains the values. Here you can see it better. When you have a term that contains the unknown, here we have Cj, this is a bilinear term, and when it has it doesn't have any unknown, in this case you see that everything is known here, because we know the function itself and we know the basis functions. So this is all known, and this is called the linear term. But I think later on we will have like the definition of these things. So then it starts to compare, and then it comes here, a very important concept, so the integration by part. If you remember from this file, it was also here that we start to integrate things. This is like applying the basis functions, so multiplying the basis functions to the equations, and then we integrate it, and then it was written here that we need to split it by integration by parts, and here is the reason. The reason is, the piecewise polynomial functions have this continuous derivative at the cell boundaries. If you remember from the previous video, when we had like a function like this, so we had like different nodes, and then we had like a function defined like this, and then another one defined like this one, and then another one like this. So at different nodes they were defined, and then if you remember, I also showed you the derivative. So the second derivative and generally the derivative are not continuous. So for terms like this one that I showed you here, for example, it is not possible to define the second derivative of the basis function because it doesn't exist. So we cannot apply the Galerkin method directly to a differential equation when such a term is in the Weck formulation. So the solution is the integration by part. And it is a very, very simple technique that you can see here, we have like a second derivative here. So it has a second derivative multiplied by v, that's the inner product. But what it tries to say here, it's maybe, it's easy to understand, but if it is a little bit complicated for you, you can imagine that, the chain rule is something like this, that you say that uv prime equals by u prime v plus uv prime. This is the chain rule. This is the derivative of a multiplication. Then this is not chain rule. Sorry. So when you have something like this, imagine instead of this we have this one. So u prime v prime. So we wanted the derivative of u prime v. It becomes something like this: u prime v plus u prime v prime. So what we have here is actually this part. So we can say that u prime v equals u prime v prime minus u prime v prime. And this is actually, I think this doesn't have v prime. Yeah, so something like this. So this is what you see here, that this one is actually this, and this one is this. So, and this is this one with the minus. So this is actually this rule, and then we we can also have like an integration on all these things, and this is what integration by part means. So what you see here is actually that. So we can say that the integration of that, because in the end these are functions, and inner product is converted to an integral. This is something we discussed in the previous video, and then an integration of these things will be converted to something like this, and we have the values at the boundaries. So, or in the file and in more advanced cases, this is always something that you can take care of using the properties of the test function space. But in this case, you can see that with having this, the second order is reduced to a first order integral, and we have the derivative of the test function of the basis functions used in a first order derivative, so we can easily solve the equation using the Galerkin method. And that's why we need integration by part, or generally that's why we need reducing the derivative order. I think you enjoy this, because this is a very, very nice fact. If you follow the previous video and this video from the beginning, we discussed the function approximated using the vectors and then the functions and then the basis functions of finite element, those kind of Lagrange polynomials in the first order, and so on and so forth. And we reach here, and now we can see that why we need to reduce the order of the differentiation in order to take advantage of the Galerkin method. And yeah, that's it. And then we apply the boundary conditions similar to what we had before to the equation, and then we can go on. I don't want to discuss the boundary condition because this is something that we usually do not deal with, because it's actually Freefem and Phoenix taking care of that using different techniques, penalty method and other techniques that they can embed the boundary conditions into formulation. But yeah, that's it. So for example, in this case with the global polynomials, this is an example. You see that this is a kind of basis function that is used in this example. So yeah, this is the basis function used, and then we have we want to solve this equation. So we know that it becomes something like this, and it means that these are integration, and we integrate it. So these are the integration for assembling A and B, and in the end we have A and B computed, and then we can solve it using any kind of solver that we want. So yeah, this is really as simple as that, and this is a nice. This is what I say that it is for a kind of notation that you can see in a lot of literature for finite element. So generally, they say that we write an equation after partial differential equation or differential equation, ordinary one, to A equals L, and that's actually something that you saw also in the Phoenix code that we had. It's a kind of standard notation for Phoenix community. A equals L, and A is a bilinear form and L is called a linear form, and that's why A contains U, which is the unknown that we want to have, and L doesn't contain it. So you can see that after integration by part, because this is the equation that we wanted to solve, after integration by part it becomes something like this. So A is this one actually, and L is this one. Really simple and very cool. And then there are some proof here, mathematical proof that the properties of bilinear and linear terms, they're not important, and in the end you will see that we have a nice notation here, A equals B. So actually this is the linear term becoming the B, and then the bilinear term contains A and the X, or in this case C. So this is a very, very important notation, and something that I said you will see a lot in finite element literature. And then there is another example here. You can have variable coefficients for equations. It doesn't matter. Later on I will discuss non-linear problems. It's a sort of non-linear one, but at the same time it can be also resolved. So when you are deriving the weak formulation, you don't need to, you deal with that. So it's something that you can easily handle. So these are, for dealing with boundary condition, and I think now these this kind of equations very well, and the things behind it. So yeah, that's it. And then it goes for these are not the things that I want to discuss, and nonlinear coefficients. Yeah. So that's it, and then it tries to implement it using SymPy and in Python. So let's go for the second Jupyter notebook, variational formulation with finite elements. So that's as simple as using finite element basis functions for psi. So, for example, if you see that we have the same equation yielding to this weak formulation or variational formulation, and then with finite elements basis function, these are the basis function that we want to use. Again, U equals the summation of C phi, and then it is very important what we choose for psi. In this case, is our phi, and phi, those Lagrange polynomials that can be computed. So it is as simple as this. This is also something that you see a lot in variational formulation. Again, A equals B, and then we go on, and based on the properties of phi function, we can have like the domain divided into points to nodes, different functions defined on each node, that is 1 in only one and 0 on the rest for each node. And then as very easily we can compute the A matrix multiplied by C equals B. And with that one, this is a comparison with finite difference. We don't want to go for that. This is very theoretical. But yeah, this is really as simple as that. So that's all you needed to know for this. I don't want to go for more computation here, because this is mostly implementation. And this is very nice to know the implementation, and you can follow it later. But actually, it is not needed when you want to work with Phoenix and FreeFM. But if you go for the implementation and implement it yourself, you can run the codes also here in the Jupyter notebook. When you see the implementation, then your knowledge will be deeper. But this is not something that you need for implementing things in FreeFM and Phoenix. One important thing is that boundary conditions are usually vanishing For the test function space, this is something that you need to know. And for example, here you see that it is, for example, on the for the test function space, here you see that v equals 0 on the boundary. So this is also something that is discussed here. But still, this is not something that I want to go to the details, because this is very theoretical, but this is an important property to always consider. So you can see that here, although this is a time dependent problem, but let's skip this one. You can see that we use the same technique to integrate an integration by part, meaning that we can have this one, and according to the properties that we have on the definition of the trial function, we can get rid of this one, and as a result, the second order derivative is already reduced to a first order one, which is this one, because this one is here and it is 0. So yeah, let me quickly scroll down to see if there is nothing that I have missed. But yeah, that's actually the concepts of variational formulation, and then you can see that it's also, there are some examples here applied to some differential equations, and then for 2D and 3D, that's the same thing, integration by part, as demonstrated in the other video and this file. But it is just the same. You have the Laplacian and you have the gradient instead of the first order and second order derivative, or sorry, the other way around. Yeah, so integration by part and everything is just the same. And yeah, so that's what you needed to know about variational formulation. And now you can see all the things connected. Now we are ready to apply this to more, let's say, advanced cases and more problems that you will see later in Tux Riders. But before that, in the next video, I will describe the process for time-dependent problems, which is quite simple. We need to combine finite difference with finite element, and then also a general overview on nonlinear problems, and then we are done. So that's all we needed to know about finite element. And then we will start to have to apply our knowledge to like free form models and Phoenix models. I hope you enjoy this, and yeah, have fun with these materials, and see you in next videos. Bye.